Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from reactive power control, and the name of the topic is STATCOM. STATCOM is nothing but a static compensator. It is a shunt connected reactive power compensation device which is capable of generating and or absorbing the reactive power, and in which the output can be varied to control the specific parameters of an electric power system. It is in general a solid state switching converter which is capable of generating or absorbing independently controllable real and reactive power at its output terminals, where it is fed from an energy source or energy storage device at its input terminal. This is the diagram of static compensator. Let's say this is your main line whose voltage is Vm at an angle theta m. This will be a transformer which is called as a coupling transformer having reactance denoted by Xt. Here this will be voltage Vsh at an angle theta sh, which is near to the converter. This will be DC to AC switching converter, and the capacitor is connected across this for exchange of a real power. So we can represent this diagram as, now instead of having this Xt as a coupling transformer, I will show this as an inductor here, which is a coupling capacitor. We can say it is a coupling transformer. Xt is the reactance. Then Vsh is the voltage near to the converter, and this will be the DC to AC switching converter with the capacitor. It will act as a variable voltage source representing DC AC converter. Now let's have a discussion about principal operation of a STATCOM and its construction. A STATCOM incorporates a voltage source inverter, or which is also called as DC to AC converter, which produces a set of three-phase AC output voltages, each of which is in phase with and coupled to the corresponding AC system voltage via a relatively small reactance, which is denoted by Xt. This small reactance is usually provided by the per phase leakage reactance of a coupling transformer. The VSI is driven by a DC storage capacitor. By regulating the magnitude of the output voltage produced, the reactive power exchange between STATCOM and the AC system can be controlled. In case of two AC sources which have the same frequency and are connected through a series reactance, the power flow will be, first will be active, which is called as real power flow from leading source to the lagging source, and second one is the reactive power flow from higher to lower voltage magnitude source. Now the exchange of the reactive power between the converter and the AC system can be controlled by varying the amplitude of three-phase output voltage VSH of the converter. So let VSH is the amplitude of the output voltage, Vm is the main line voltage, or it is also called as AC system voltage. Now we know that already we have gone through this relation P equal to Vs into Vr upon X into sine delta. This was the relation that we already derived in this unit only. So active power is given by PSH will be equal to Vm into Vsh upon Xt. Xt is the reactance, sine of theta sh minus theta m. And similarly, we can write an expression for the reactive power which will be equal to QSH is Vm Vsh upon Xt cos of theta sh minus theta m minus Vm square upon Xt. Now what happens if your theta sh and theta m will be the same? So if you put theta sh equal to theta m in equation PSH, then what you will get? You will get answer as a 0, because the term was sine of theta sh minus theta m. So sine, this will be equal, means what? Theta sh minus theta m will be equal to 0, and sine 0 is equal to 0. So therefore your PSH active power will be equal to 0. And reactive power under this condition can be represented as QSH will be equal to Vm Vsh upon Xt. Now here after that there was a term cos of theta sh minus theta m, but as theta sh equal to theta m, so cos of 0 will be equal to 1. So that's why this term is not there here. So we will get qsh equal to what? Vm vsh upon xt minus Vm square upon xt. So if I take a Vm common here, then I will get this expression. What expression I will get? Vm upon xt into bracket Vsh minus Vm. So from this equation, whatever equation here we have written for a QSH, we can get three conditions. What are that three conditions? Let's discuss. If the amplitude of the voltage VSH is greater than Vm, then what you will observe? Please remember the diagram. Now as VSH is near to the converter, so I can draw it here. This is your VSH near to this converter. Here the capacitor is connected. Here there will be a transformer reactance and this will be a line voltage which is Vm. So if VSH is greater than Vm, then what will observe? The direction of the current will be like this. It will from higher potential to lower potential. So current will flow from converter, that is this is your DC to AC converter, to the AC system through a tie line reactance. So therefore we can say a converter generates the reactive. Now which will be? That will be a capacitive reactive power for the AC system, or simply we can say that the reactive power is injected into the system. Now the second one is, suppose Vm is greater than VSH, second case. So the direction of the current will be exactly opposite. It will be from upper side to lower side, or you can say from main line to the converter. So the current flows from AC system to the converter through a tie line reactance. So with respect to converter, I can write the statement as converter will absorb the reactive power. Now it will be what? It will be inductive reactive power, or reactive power is drawn from the system. And when VSH will be equal to Vm, that is there is no fault, then no current will flow through this and there will not be any exchange of reactive power. Now adjusting the phase shift between converter output voltage and the AC system voltage can similarly control the real power exchange between the converter and the AC system. So in other words, we can say that the converter can supply real power to the AC system from its DC energy storage if the converter output voltage is made to lead to the AC system voltage. And similarly, if the converter output voltage, that is VSH, is made to lead to the AC system voltage, that is Vm, meaning is nothing but what? Your angle theta sh is greater than theta m, then the equation of the PSH which was discussed earlier, it will become a positive. Then the converter can supply real power to the AC system from its DC energy storage. And if the voltage will lag behind the AC system voltage, meaning is nothing but if the angle theta sh is less than theta m, the equation of the PSH will become negative, then it will absorb a real power from AC system for the DC system. Now let's have a look for a VI characteristic. So this is what is the VI characteristic of the STATCOM. So here if you see, whatever this line will indicate that it is maximum turn-off capability of the converter switches, and this line will indicate a junction temperature of the converter switches. On y-axis we have taken Vt, and on x-axis we have a current with both the regions, capacitive region and inductive region. So STATCOM can supply both the capacitive and the inductive compensation, and it is able to independently control its output current over the rated maximum capacitive or inductive range irrespective of amount of the AC system voltage. That is, the STATCOM can provide a full capacitive reactive power at any system voltage even as low as 0.15 per unit. So this is what is the VI characteristic of a STATCOM. So in this video, we discussed about working principle, construction and VI characteristic of the STATCOM. Thank you for watching this video.